Ever wished your emails could write themselves? That's the magic of Autocompose. This intelligent autocomplete feature, found in apps like Gmail, leverages cutting-edge AI to predict what you're about to type, helping you write faster and more efficiently. We'll explore its foundation in large language models, how it learns from vast datasets, and the engineering challenges of providing real-time, accurate suggestions at a massive scale. So how does Autocompose know what to suggest? It all begins with an enormous amount of data. At the heart of this intelligent feature is a sophisticated large language model, or LLM, which needs to learn. Think of it like a student learning from textbooks. Our first step shows the massive email datasets, which are anonymized email conversations, billions of them, serving as the ultimate learning material. This data is then fed into an LLM training cluster, a powerful group of specialized computers equipped with graphics processing units, or GPUs, designed to process this vast amount of information. This cluster diligently trains on billions of emails, meticulously analyzing patterns, common phrases, and grammatical structures. Once the LLM training cluster has finished its intensive learning process, it outputs a trained model. This isn't just data anymore. It's an intelligent artifact, represented here as the trained LLM model. Think of it as the brain of our Autocompose, now filled with all the knowledge it gained from those billions of emails. But where do we keep this valuable brain? It's sent to a model repository, which acts like a secure digital library, efficiently stores model versions. This ensures that our trained model is safely preserved and ready for deployment. Now that our intelligent trained LLM model is safely stored in the model repository, it's time to make it available for real-time predictions. This is where the prediction service comes in. This service acts like a dedicated express delivery system, responsible for taking the trained model and making it operational. It efficiently deploys model from the repository onto its own servers. This preparation is crucial because it needs to be ready to serve millions of users with incredibly low latency. Now, let's bring the user into the picture. Imagine you, as the user client, are typing an email. You start with the phrase, "I am looking for." What do you think happens first when you begin typing? The magic of Autocompose is about to unfold. As you type, your client application doesn't wait for you to finish the sentence. Instead, it continuously sends prefix for prediction to our waiting prediction service. This is happening in milliseconds, behind the scenes. This is the thrilling part. Once the prediction service receives your text prefix, "I am looking for," it quickly consults the trained LLM model it has deployed. Accessing its vast learned knowledge, the LLM analyzes the context and, based on statistical likelihood from its training, predicts the most probable next phrase. Almost instantly, the prediction service returns suggestion a new job back to your user client. This entire round trip, from your keyboard to the LLM and back, happens in milliseconds, making it feel like the system is reading your mind. This is how modern web applications create seamless user experiences at scale. Imagine you're composing an important email, and as you type, you expect intelligent suggestions to appear almost instantly, like magic. This seemingly simple action kicks off a complex dance behind the scenes. Let's start with you, the user, eagerly typing away. Now, what happens to your keystrokes? They don't just go to a single computer. Your concurrent request, along with millions of others, first hits a load balancer. Think of this as a super efficient traffic cop that directs each request to the best available server, ensuring no single server gets overwhelmed and your suggestion arrives quickly. Once the load balancer directs your request, it lands on one of many distributed prediction service instances. These aren't just one server, they are a vast network, often located geographically closer to you. Each instance houses a smaller, optimized version of the powerful machine learning model. To make things even faster, each instance has its local cache, storing frequently requested phrases and common suggestions. This is like having a cheat sheet for popular answers, ready to go. These distributed prediction services don't work in isolation. They frequently sync with a global model store, which holds the massive, constantly updated large language models LLMs trained on enormous datasets of text. This is the ultimate source of knowledge. Once a prediction service generates a suggestion, perhaps a new job when you type 1 I'm looking for, it's sent back to you with incredible speed, aiming for less than 100 milliseconds. This almost instant feedback is crucial for a smooth writing experience. Bringing it all together, the biggest feat of Smart Compose is not just making predictions, but doing it for millions of users, making billions of predictions daily. This demands incredibly robust load balancing, intelligent caching strategies, and highly optimized machine learning inference techniques. Every component, from the load balancer to the distributed prediction engines and their local caches, works in concert to ensure your writing flows seamlessly, making that I am looking for a new job suggestion appear as if by magic. This is truly the power of modern distributed systems at a global scale.